Hello friends, welcome back to the tetrahedron chemistry classes. So guys, in today's class I am going to discuss the S block elements, and these S block elements are also known as the alkali metals, and these alkali metals or the S block elements are placed at the extreme left end of the periodic table. So this is their first group, right, which starts from the hydrogen. However, the position of the hydrogen is still actually the confusing. So basically we can start with this lithium and goes up to the francium. This lithium, sodium, potassium, rubidium, cesium and francium, this forms actually the alkali metal group. While the second one, which starts from the beryllium and goes up to the radium, it is your alkali earth metal group, and I will discuss this alkali earth metal in the later classes. Okay, so in today's class I am going to discuss only the alkali metals. So why these S block elements are known as the alkali metals, right? When we dissolve these alkali metals, they form the hydroxides, and that hydroxide solution of these alkali metals is quite alkaline in nature. That's why these elements are known as the alkali metals. Okay, so what are the S block elements? First of all, you can see here, this is actually the first A group which I have shown you here. If I go back, right, so this is your first A group, or simply you can say it is the first group, right? So as you can see here, elements of the first A, the alkali metals, right, and the second A, which are the alkaline earth metals. We will discuss these alkaline earth metals in the subsequent lectures. Okay, so these basically two constitute the S block elements, and their outermost shell electrons are actually present in the s orbital, right? If you want to know, then say if you write the any configuration, for example I am writing the configuration for the lithium. You know the lithium is 3. Okay, so it is what, 1s2, and this is actually the 2s1, and you know the capacity of s orbital is actually to accommodate only 2 electrons. Since only 2 electrons can go into the s orbital, right? So that's why only 2 groups are there for the S block elements, because only 2 electrons can go into the s orbitals. That's why only two S block groups are there. First is your alkali metal and second is the alkaline earth metal. There is no problem in that. Okay, so this is the way you can say actually how many groups are possible in case of the S block elements, right? Similarly, if you want to know, say if I go back, right, see at the right end you can see here, this is the P block element, right? So here you can see 1, 2, 3, 4, 5, 6. So total 6 groups are there when you talk about the P block elements. And why is it so? Because you know, when you have your p orbital, so p orbital actually maximum can accommodate 6 electrons, right? So if it can accommodate 6 electrons, which gradually fills actually, that's why this actually your p block elements is having the 6 group, right? You can understand the things like that only. So now you can see here, as I already told you, this hydrogen properties are much similar to the alkali earth metals and hence the halogen family. So it's exception case in case of the alkali metal. It should be the alkali metals, not alkaline earth metals, right? Please remember this thing. Okay. Now the next thing is that how where actually they can occur. What should be the occurrence for this, right? So here you can see the occurrence of the group 1 metals. So they are the very reactive one. Please remember this one. This basically this sodium and potassium. Now group is like that, you know. I have already written like this is lithium, okay, and then sodium and then potassium. This is your rubidium. This is R, and then your cesium and then your francium, just like that. Okay. So out of these two, you see, you can see as sodium and potassium, right? This sodium and this potassium, they are actually quite abundant in nature. Their concentration in the nature is very high, right? Their concentration is very high. right? Say somewhere around, if you check your biosphere, so nearly 2.6% of sodium abundance is there, and your potassium is nearly 2.4% abundant in the nature. You should know this thing. Okay, so for the occurrence, you should remember this thing, that your sodium and potassium, if you follow this, right, is if your sodium and your potassium, they are the 6th and the 7th most abundant. So basically this is your 6th most abundant metal, and this potassium is the 7th most abundant element in the earth crust, basically, right? And among all the alkali metals, the less electropositive lithium, right? Please remember, the size of the lithium is very small. Okay, so it is less electropositive, so I can write it here, it is less electropositive. However, I will discuss the anomalous behavior of lithium in pretty much detail, but right now you can understand, out of all the alkali metals, lithium is actually your less electropositive, right? That's why it is found in the nature as silicates. So please remember this point. This is very important for your examination point of view. Lithium silicates, okay, because it is less electropositive, right? When it is less electropositive, due to its smaller size, it forms actually the silicates, okay, while other elements, right, if you talk about these from sodium up to cesium, actually, okay, so they generally form the chlorides, okay, alkali metals, chlorides, okay. Please remember this thing, okay. And your compounds of sodium and potassium are the most abundant compound in the nature, while remaining alkali metals occur in the nature very rarely, okay. However, you know this francium is radioactive. Please remember it is, so it's actually decay by its own, and it is very short lived. And you can see here, this sodium and potassium, I already told you. Lithium and rubidium, they are less abundant. Cesium and francium, more specific, not cesium, but more cesium, though it is having the little of radioactivity, but francium is actually basically a radioactive material, and it decays like that, and its half-life is actually the 21 minutes only. So this is the occurrence which you should know. Now moving to the next slide. Okay, ores. What kind of the ores are present in the nature? This is again a very important question for your competitive examination as well as for your school examination in +2 examination, right? So your spodumene is actually the source of the lithium, which forms which actually occurs in the nature as lithium aluminum silicate. As I already told you, this lithium is very less electropositive, so it forms the silicate, okay. Then second one is the petalite. Petalite is again the lithium silicate, which is the source of the lithium again. And if you go for the source of the sodium, then the common salt or the rock salt, which is the NaCl, the table salt actually, which you commonly use in your house, actually is the main source of the sodium, okay. Then sodium carbonate is there, which is another ore like Na2CO3, again the very important one. Then sodium sulfate, which is also known as the sodium sulfate is Na2SO4. When it is having the water of crystallization, 10 moles of the water of crystallization, then it is known as the Glauber's salt. So this is again a very important question for your examination point of view. What is the formula of the Glauber's salt? The formula of the Glauber's salt is the Na2SO4, right, with 10 water of crystallization. Then cryolite is also there, which is the source of their sodium, and then borax is also there, right, which is again the hydrated form of this borax. 10 water molecules are there. Then sylvine, which is the source of the potassium, that is KCl. Then carnallite, again this is the source of their potassium chloride. It is kind of a double salt, right? It is present along with the magnesium chloride. And then feldspar, with this feldspar is very common, which is the source of the potassium again, and it is again the potassium oxide and the aluminum oxide silicate. It is the double salt. So this is your double salt. The 9th one, which is carnallite one, and 10th one feldspar is the double salt, right? Remaining all are the single salts. Okay, so this is the occurrence, and you should remember the formula and name of these ores, right, of the group 1 metals or the alkali metals. And then if you go for the electronic configuration, guys, electronic configuration is very important. You see the lithium is here, So my suggestion is that you should remember actually your magic numbers which you have actually started learning in your class 8th or 9th, I think, right? And the magic numbers are 82, 88, 18 and 32, right? If you know the atomic number of the first element of the group in the periodic table, of any group in the periodic table, right? If you know or if you remember the first element of any group of the periodic table, then you can assign the atomic number to the remaining of the group members by using this magic number trick. Okay, so what is the magic number trick? You can see here, this is my lithium, and lithium is 3, and this 3 is greater than 2. So what you can do, after lithium you are having this sodium, and if you add 8 to the sodium, so 3 plus 8, this will give you 11. Now this is 11 your sodium, and again if you add 8 to the 11, then you get the 19, right, which is the atomic number of the potassium. And if you add 18 to the 19, then you will get the 37, which is the atomic number of the rubidium. And if you add another 18 to 37, you will get the atomic number of the cesium. And if you add the 32 to this 55, you will get the 87, which is the atomic number of the francium. So by using this magic number trick, you can remember, or you can remember the atomic number of the remaining elements of the group. So here you can see I have given you the trick also, right? Just like that you can see. However, these slides are not actually prepared by me. I have downloaded this slide from the internet, right? Some Deepa Sharma, the credit goes to some Professor Deepa Sharma. I am using the slide of her actually, okay? But I have also added my own slides, right, and my own literature to this one, right? So if you write the electronic configuration for this 3, so this will give you the 2s1, and this is the configuration of the helium, right? So if you are the beginner here and you don't have the much idea about how to write, so I can write here lithium, which is the atomic number of 3, and I can write 1s2 and 2s1, right? And if you know the helium, actually helium is what? 2. So helium is nothing but 1s2. So if you combine all these two, right, so lithium, the electronic configuration of the lithium can be written as the electronic configuration of the helium, just like that, and 2s1. So what I did actually, I replaced this 1s2 with the helium actually, right? So and it is very important to put this helium into the square bracket actually in order to show the noble gas configuration. Okay, similarly if you go for the sodium, right, this is your sodium. I am writing the electronic configuration of the sodium. Sodium is what? 1s2, 2s2 and 2p6 and the 3s1. Because these are the s block elements, then it is mandatory that the last electron will go into the s orbital. Okay, and now if you check the electronic configuration of your say neon is 10. So it is 1s2, 2s2, 2p6, and here you can write 3s1, just like that. Oh, sorry, no, 3s is not there. Only 10 electrons are there. Okay. So now if you compare, you see here 1s2, 2s2, 2p6, that means up to this, right? This part is very, very common. See, if you compare these, so this is very common, right? So what I can do, I can write sodium like that, Na11, that is electronic configuration of the neon in the square bracket, it is very important, right? And then you can write 3s1. So this is the electronic configuration of sodium. So on the similar node, you can assign, you can write the electronic configuration of the remaining elements, right? For potassium 19, you can write the argon and 4s1, and for your rubidium, you can write rubidium 37. You can write the your krypton 5 and 5s1, and for cesium 55, you can write the xenon 6s1, and for francium 87, you can write the radon 7s1. So it is, you can see here 2, 3, 4, 5, 6, 7. That means the principal quantum number is changing, and you know, whenever you write the electronic configuration, so this actually the prefix 1 and 2, this is actually the principal quantum number. So as you move down the group, the principal quantum number increases. That means the size of the alkali metal increases. So later I will come to the size also, but you should remember whenever we move down the group, the size of the alkali metal increases, right? In case of, not for the alkali, it is not only true for the alkali metal, it is true for your alkaline earth metals and the p block elements as well. Okay, but d block elements are somewhat different, lots of exceptions are there, right? I'm not going to discuss the d block elements because I have discussed the coordination chemistry in the pretty much detail. I have a playlist actually for the coordination chemistry. If you are watching this video for the first time and you are interested in the coordination chemistry, then you can search in the search bar of the YouTube coordination chemistry by tetrahedron chemistry classes. Then you will find my playlist there. I have uploaded a detailed 40 or 42 lectures in there. Okay, so now next is what? This is the electronic configuration, which is very very important, and you should know about each and everything, how to write the electronic configuration of this. Okay, and then see, if you want to see, if you make the positive ion for this one, Li positive, Na positive, K positive, right? Say I can write like that. Say if I make the Li positive, that means lithium ion. If I can make the sodium ion, then potassium ion, right? And then if I write the rubidium ion, then the cesium ion, and then the francium ion. Okay, if I write like that, so I have removed one of the electron from the outermost shell, right? So what result actually I am getting? I am getting the noble gas configuration. This is for helium, okay, and this is for neon, and after neon this is your argon, then your krypton, then your xenon, then your radon, right? So this is very very important. So and you know, only one electron is present here, only see, as you can see here, only one electron is present here, so you can remove one electron very easily from them, right? That's why they show, the alkali metal shows the +1 oxidation state. So the relatively very simple chemistry of the alkali metal is probably due to the ease with which their valence electron can be lost from the outermost cell in order to achieve the noble gas configuration. Physical appearance, that means if you look at the crystal structure of these alkali metals, how they look like actually, right? It is something very very important. So first of all, you should know this very important thing. These alkali metals, I am writing here, alkali metals, right? If you cut them with the knife, they are very soft. These alkali metals are very soft. You can cut these alkali metals with the help of the knife or the blade actually, right? So if you can cut them, right, so they actually give you the silvery shining or silvery shining, right? That means they shine like the silver. So they all are actually, right? So starting from the lithium up to the francium, they all are the silvery white solid. So I can write, and they are so soft that they can be easily be cutted with the help of the knife or the blade or any the sharp things. And why actually these are very very why alkali metals are soft? See, the iron is the very famous metal which is very very hard actually, and other metals like they are also hard, but these alkali metals are very very soft. Okay, and what is the reason of the softness? And the reason of the softness, you can see, if you go back here, you can see only one electron is present. Okay, that means this is the bonding electron. So very less, only one bonding electron is there. So the metallic bond in case of the alkali metal is very very weak, and due to this weak metallic bonding, your alkali metals are soft in nature. Right? If you start from the lithium and go for the sodium and then potassium and so on, right? I can write francium here. Actually softness increases. Okay, so this softness actually increases down the group as the number of the non-bonding electrons down the group increases. The repulsion between them will actually decrease the cohesive forces. It is increases. So softness increases down the group. This is something very very important. Sodium is 11, and here I am writing here sodium positive. That means you have removed one electron. That means it is having only 10 electrons. So the electronic configuration is like that. if somehow I removed one electron from it, okay, by supplying some amount of the energy to it. So I'll convert this sodium into the sodium ion, and sodium ion is having only 10 positive, 10 electrons only, right? Not positive, 10 electrons only. So here you can see where if you fill the 10 electrons in this sodium ion, then your 3s subshell will vanish. It will go away from there. That means third shell actually, right? The principal quantum number third will vanish from here. That means its size decreases. Okay, you can understand like that in that. See, if you are very beginner here, if you are in junior classes, and say if you are actually your 10th class student or the 9th class student is following this particular lecture, so for them actually, for such students, I can write like that. This is your sodium, say this is sodium nucleus, and this is your first shell, okay, and this is your second shell, okay. So basically this is n equals to principal quantum number 1, and n equals to principal quantum number 2, and n equals to principal quantum number 3. Okay, so I can write the third one here. 8 electrons in this one, 3, 4, 5, 6, 7, 8, and 1 electron is here. And if you remove 1 electron from here, so what will happen? You will end up in the sodium positive. So if you fill the electron again, 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. So in that case you can clearly see when you remove 1 electron from here, the 3s shell actually vanishes. It goes away actually, or you left with this one. So that's why your cation is smaller than the parent atom. So you should remember this one for the alkali metal especially, or for the alkaline earth metal also, right? Your M positive ion is always smaller in size for M, right? The implication is that your sodium ion will always be bigger than your, so your sodium atom is always be bigger than the sodium ion, and this is also true for the potassium. Potassium is also bigger than your potassium ion, right? You should know this thing, okay? So the atomic or the ionic radii of the alkali metals, they are the largest in the entire periodic table, right? And increases down the group. So please remember, when you go down the group, size increases. Size increases means the atomic radii or the ionic radii increases. And why is it so? And answer, you can go for the answer, you can go back. Here you can see the principal quantum number actually increases. Here the principal quantum number is 2, here the principal quantum number is 3. If you keep on going down, then your principal quantum number increases. That means the shell increases. Shell increases means that means you may have one more layer. If you go for the potassium, then again one more layer, so the size increases. So when you goes down the group, the size, whether it is atomic or the ionic radii, it is always increasing. All the alkali metals, they are actually having very low density. So whether your say lithium is there, okay, your sodium is there, your potassium is there, especially I am talking all about these, right? So they are having not only these, all remaining members also, right? Lithium, sodium, potassium, rubidium, cesium, francium, they all are having the very low density, but especially these three, they are less denser than water. The implication is that if you put these metals, if you put these metals into the water, it will not actually go down into the water. It will not actually go to the bottom of the water. It will float over the surface, or these metals will float over the surface of the water. However, it is not recommended. It is not recommended that to add these metals into the water, because it is very dangerous and accident may occur. Go down the group actually, right? So density increase. But again, you can see a very important thing is that it is important to put the data here actually for the density. So I am writing here, say and if you go for the data wise, right? So it is not, however, it is not very important for you to remember the data. I'm having the data with me, that's why I'm putting here. 0.534 is the density of the lithium, and it is at 20 degrees centigrade. Okay, this density, if you change the temperature, the density also changes. You know the density is the function of the temperature. Okay, and for sodium it is 972 gram per cc, and for potassium it is 0.859 gram per cc, and for cesium 37 it is 1.53 gram per cc, and for cesium it is 1.9 gram per cc. So you can see here it is less denser. If you go here, the density increases. That means, and I already told you the density increases down the group. That means this potassium should have more density than this sodium, right? But this is not happening, right? This is not happening here. And what should be the reason behind this? So this is the very important exceptional question for you. That means potassium has lower density than sodium. Why? Another very important question. So the simple answer is that this is due to the abnormal increase in the volume of the potassium. Okay, so if you write the volume of these two, sodium and potassium, right, atomic volume, molar volume, if you write here, so for sodium it is, the value is 23.68, okay, centimeter cube per mole, and here you can see it is for potassium it is 45.36. so this actually increase is of roughly 22 units. This increase is of roughly 22 units. So this is actually abrupt change in volume, right? And this abrupt, and you know, see, if you write here density equals to mass over volume. So when volume increases, density decreases, right? And this abrupt increase in the volume of the potassium decreases the density of the potassium when compared to the sodium, right? However, here if you go for the, if you compare the molar volume of potassium and rubidium, large, see, increment is there, but that increment is not that heavy or that high, right? That's why this behavior is there. So it is very, very important why potassium has the lower density than the sodium. It is because abnormal increase in the volume of the potassium. And again you can see that due to the presence of the d orbitals, potassium has low density. It is very important to note that when we go down the group, the atomic size as well as the atomic mass both increases. If you go down the group, atomic size as well as the atomic mass both increases, but increase in the atomic mass is more dominant. But in case of the potassium, right, reverse is happening here. In case of the potassium, increment in the volume is too much, is very, very high, right, then the atomic mass. So in that case, in case of the potassium, your atomic volume actually, the size actually the dominant factor, which decreases the density of the potassium. You should remember this very important thing. Okay, now moving to the next slide. See guys, I'm actually giving this, I am providing this lecture for the students who are studying in the class 11, and it is also equally important for the students who are going to prepare your JEE mains examinations, right, or for your CSIR net or the GATE examinations, right, or in the IIT JAM examinations. Sometimes whatever we study in the JEE, for the JEE preparation, the questions actually comes in the other competitive examinations also. So it is very important for you to focus very carefully, and simultaneously what you can do, you can make your notes. And melting and boiling point decreases down the group. Melting and boiling point decreases down the group. So what, there should be some reason behind this, na? Why the melting and the boiling point decreases down the group. There should be some reason behind this. So what is the reason? So the reason for their low melting in the boiling point is the presence of the weak intermetallic bond, right? Say for example, if you are having K2, right, or say you are having the Na2. So in case of the Na and Na, two Na atoms, okay, so there would be the metallic bond, and you know the only one electron is involved, so this metallic bond is very, very weak, okay, and the weakness of the metallic bond increases when we move down the group. That's why the melting and boiling point also increases, because see, when the size increases, the weakness of the bond also increases according to the size. And you know, if you go for the lithium, sodium, potassium, rubidium, size increases down the group. When size increases, that means the metallic bond strength decreases. That's why the melting and boiling points, both things actually, right? We can correlate the melting or the boiling points, both things with this, right? This is something very, very important. Later I will come to this point also, whether we can form this K2 positive or L2 positive, or your say RB2 positive type of the diatomic actually metals, right? I'll come to this particular point also. Another very important thing. You know what is the modern definition of the metals? That means the elements which can easily remove electrons from them, or electrons from their outermost shell, they are the metal. That means they form the positive ions. And you know, all the alkali metals, if I write the alkali metals with the M, they very readily lose the 1 mole of the electrons to form one positive over there, right? M positive. If you lose the 1 electron from here, okay, it will form the M positive. That means they are metallic in nature, okay. And if they are metallic in nature, and you know the metal are having luster, and in few moments back or few minutes back I already told you, all these metals are what? They are white silvery solid, okay. So there should be the metallic luster in them, okay. So metallic luster. So why this metallic luster is there? This is another very, very important question, very important one, especially for the beginners. It is very, very important, okay. So first of all, you should remember this particular point. Alkali metals are the most electropositive elements in the entire periodic table, and their metallic character increases down the group. Again say, if you go down the group, so metallic nature increases. Why increases metallic nature? As you know, the size, when you move down the group, the size of the element increases. That means there would be less interactions or less attraction between the nucleus and the outermost electron. That means the effective nuclear charge, when you goes down the group, the effective nuclear charge decreases, which sets the outermost electrons rather loosely bound to the nucleus. That means you can very easily remove from them, right? And when you can easily remove the electron from them, that means the metallic nature increases down the group. You should remember this particular point, right? These all are the metals, and thus they are the very good conductors of the heat and the electricity. So it is again very important point. Good conductor, they are good. Alkali metals are good conductors of heat and electricity. They also showing the metallic luster, as I already told you. So spelling is little bit wrong here, okay. Metallic luster, and the reason for the metallic luster is quite simple. So what is happening? See, in my lecture of the coordination chemistry, I already told you that the electronic transitions, the concept of the electronic transitions, the colors and all these things, right? But for the beginners, right, why this luster is there? There's something very, very important. You know, all the alkali metals, they possess the metallic luster, and especially when you cut, right? When you cut these alkali metals, so freshly cut metals actually is having the free electrons. See, electrons are already there, but when you cut the metal, then your free electrons are exposed to the environment, right? And they absorb the energy, right? They absorb the energy from the sunlight, and the electronic transition will occur. They move to the higher conduction band, and from them they are falling back, and when they are falling back, they are emitting certain kind of the energy, or that energy or that radiations actually fall on the your visible region, right? And you observe the color or the metallic luster. So basically the presence of the free electrons which undergoes the transitions, and when they fall back into the ground state, they re-emit that particular light which fall on the visible range, and this is the reason for the metallic luster. This is something very, very important. And now the very, very important aspect, and which is the flame coloration. That means when you burn the alkali metal chlorides, right? Say generally first of all what you do, you convert your metal into the metal chlorides, and then metal chlorides is actually subjected to the flame, and that flame, when these compounds burn, they actually give the color. Okay, this is something very important which you should know. Okay, and what is happening here, you see both groups show the flame coloration. So I am not going for the both groups, I am only going for the alkali metals here. The electron present in an atom absorb energy from the flame, and their electrons are excited to the higher energy level, which is the simple concept. When these electrons fall back to the ground state, emit radiations of the different wavelength, and this emitted radiations falls on the visible region, which gives the color to the flame. Again, see guys, please remember, don't get confused. Earlier I have given you the example that why they are lustrous in nature, why metallic luster is there. I have used the same concept of the electronic transitions. When you cut the metal and the electrons absorb fresh light, actually sunlight, and then the electronic transition will occur, and thus they appear as the lustery white or silvery white solid. But here you can see the different colors are there. So color is not for the pure metals, but this color is for the metal halides, alkali metal halides. Please remember this point. Okay, so please remember this point. So here you see here lithium chloride. If you have the lithium chloride, so it is give you the crimson red color, and crimson red, that means you have to identify the color also. So and for NaCl, if you see here, so it is actually shining in yellow color. It is basically golden yellow. Okay, and if you subject your potassium chloride to the flame, if you introduce the potassium chloride to the flame, then you will have the violet color, but that violet color is not very sharp. It is the pale violet in nature. And for rubidium chloride, this color is actually purple. Okay, it is purple. And for cesium chloride, it is the sky blue. Okay, so here I already shown you these colors actually, right? This is something very important. फ्रांशियम की बात इसलिए नहीं करते क्योंकि रेडियो एक्टिव है, उसका कोई फ्लेम कलरेशन नहीं होता है. सो दिस your francium, actually we are not introducing here, so because it is radioactive in nature, it will not give any color to the flame. This is something very important. Please remember, the vapors of the alkali metals, especially in the form of the chlorides, basically imparts the characteristic color to the flame. The reason for this color is that the loosely bound electrons get excited on heating and jumps to the higher energy level, and from that higher energy levels they fall back into the ground state and they emit the energy of the energy, and that energy falls in the visible region, which gives the characteristic color. Okay, now the next thing is the hydration energy. This is another very important concept, and from this particular concept you may find lots of the question in your competitive examination, right, especially in the competition. Okay, however, the concept of this hydration energy in case of the coordination compound I have explained in my coordination chemistry lecture, but again I am going to repeat that thing here. So first of all, you should know what is actually the hydration energy. Okay, so here see, I don't know, yes, it is written here. Hydration is what? Hydration reaction is the chemical reaction in which a substance combines with the water. The process is known as the hydration. Hydration enthalpy or the hydration energy is the amount of the energy released when 1 mole of the aqueous ions is formed from the gaseous ions. Please remember, or another way of giving the definition of the your hydration enthalpy or the hydration energy is that the heat energy released when new bonds are formed between the ions and the water molecules. That means whatever your ion is present here, say if I can write here, say if M positive ion is there and say water molecule is there, okay, and when they form actually the bond between them, right, so when they form the bond between them, okay, so this is basically this process actually occurs by the release by the release of the energy. That released energy is the hydration energy. That's why I said, I gave the statement that the heat energy released when new bonds are made between the ions and the water molecules. Please remember this particular thing, very important, very important. And because energy is releasing from the system, that means this hydration enthalpy is always negative. Please remember, it is always negative. Hydration enthalpy is always negative, always negative. However, it is not very important to remember or to learn the values. Okay, so here what is happening here, you can see this is the sodium ion. Okay, and this sodium ion is having the positive charge, and this is your water molecule, right? This water molecule, and you know the water molecule is polar in nature, so you can write positive on the hydrogen, positive on the hydrogen, and 2 negative or 2 delta negative on the oxygen. So this actually negative dipole interacts. See, this will not form any bond. Please, you cannot think like that the sodium ion is going to form a covalent bond or the ionic bond with it. It is only the interaction between the dipoles. Please remember. Okay, and this is get hydrated. Hydrated means water molecules will surround it, right? And during this process, lots of energy is released. That means the reaction is the exothermic, and that released energy is the your hydration energy. So if you want to know this concept of hydration energy in pretty much detail, then you should remember this thing, hydration enthalpy. I am writing here enthalpy. Okay, this is your hydration enthalpy, and that hydration enthalpy is directly proportional to the charge present on the metal. And you know hydration enthalpy is also, it is inversely proportional to the size of the metal. Please remember. And you know when you are discussing the charge, and you know for the alkali metals charge is always positive, because your lithium is positive, your sodium is positive, okay, your potassium is positive, right, your rubidium is positive, your cesium is positive. That means in that case of the alkali metals, you are not comparing this alkali metals with the alkali metal alkaline earth metals. Actually you are not comparing. So if when you are not comparing, and if the charge is same, that means it will not make any difference. So what I can do, I can remove this part from here. So from here you can clearly observe your hydration enthalpy is inversely proportional to the size. That means when the size increases, the hydration enthalpy decreases. That's why if you go down the group, hydration enthalpy, so I can write that hydration enthalpy is delta H hydration, it is decreases. It is decreases. So you should remember this thing, right? That means hydration energy would be higher for this lithium, okay, and it goes on decreasing when you go down the group. This is something very, very important, right? You should remember this particular point. This is something very, very important. So here what you can do, you can write, if you want, then you can write for Li positive, hydrogen enthalpy is maximum, and this is for sodium. It follows the same regular pattern actually. Okay, then rubidium, and then here cesium. Francium we cannot include actually. Okay, this is something very, very important. Lithium positive ion has lowest ionic mobility. Lowest ionic mobility among alkali metals. Why it is happening? ऐसा क्यों हो रहा है? ठीक है? So why this lithium? See, it is having the smallest size. That means it is heavily hydrated. Heavily hydrated. That means it is not free to move here and there due to the interaction with the water molecules which surrounds this lithium positive ion. That's why it is having the lowest mobility in the aqueous solution. Please remember this point. If you are going for the mobility of the ions, then the lithium in the aqueous solution especially, then the lithium would be the least mobile. Lithium ion would be the least mobile, and your cesium ion would be the most mobile in the aqueous solution. Okay, I hope you understood the things actually, right? It is also always having the negative value. It is also written here actually. I missed this thing. Okay, next is okay, hydration energy. I have already explained to you all these things. This is the periodic variation, just like that. Size, right? You can see the biggest, it is the minimum. Hydration energy. See, this thing I have already explained you in the last slide, so there is no point of going or explaining the same thing again and again. Moving further. Again, this is the value of the hydration enthalpy. It is in the kilojoule per mole, right? So it is going like that. You can see here. Okay, so here you can see the value actually goes on decreasing when you move down the group. This is something very important. Don't get confused like that. It is having the negative value, and this negative value actually is the bigger than minus 1519 actually, right? So if you follow this one, then this will look bigger. It is not like that. Ignore the sign actually. However, this is always the negative with sign, but there is no mathematical explanation for this one. Okay, you cannot understand in the mathematical way, otherwise you will end up with the confusion that means your cesium is having the higher hydration enthalpy. It is not having the higher hydration enthalpy, only the sign is negative. Okay, next is okay, oxidation and reducing agent. Again, a very important thing is there, and that thing is the oxidation and the reducing agent. So it's very easy, you know. It is having very low ionization potential. These alkali metals are having the very low ionization potential, so they can very easily remove one electron from it, so they easily undergo the oxidation. And the species which undergoes the oxidation, they act as the reducing agent. Please remember this particular point. So I am only discussing the alkali metals. You can ignore this alkaline earth metals. So for these alkaline earth metals, what I can do, I can cut it from here. Only focus on this one. Okay, so alkali metals, they readily lose one electron, right? So just like that. So they are very good reducing agents. They are very good reducing agent. Please remember this point. They are very good reducing agent. Okay, and when they generally they forms the special type of the reducing agents also. I'll discuss those things also in a little while, but you should know this thing. Because they have the strong tendency to lose the electrons, s electrons, so they are the very powerful reducing agents. Okay, and if you in the aqueous solution, right, if you go in the aqueous solution, so in the aqueous solution, your lithium, right, your lithium is the strong reducing agent as compared to the cesium. This is something very important. Again, this concept is due to the your hydration energy, right? Your hydration energy, you know, high hydration energy for this lithium ion, is hydration energy is very high, and that high hydration energy compensates the ionization potential, high ionization potential energy. That's why this behavior is there. Okay, and if you see, this order is already given here, but you should remember this particular thing, very important. These alkali metals, they are very strong reducing agents. So guys, now let's move on to the chemical properties of the alkali metals. Okay, so in that case, first of all, we are going to look for the chemical property, which is nothing but the reaction with the water or the moisture present in the atmosphere, right? In both ways actually, if you treat these metals with the water, or if they absorb moisture from the water, the reaction actually happens in the same way. So here I have written the metal M, so I have generalized the reaction. Okay, so you can write, instead of this M, you can write your potassium or sodium, etc., all these things. And when these metals reacts with the water, they form the hydroxides, right? And these hydroxides are basic in nature. That's why these metals are also known as the alkali metals. And of course, they will remove the hydrogen gas from here. So it is very important, you know, the certain metals which, when you put on the water or on the dilute acid, they remove the hydrogen gas. And here you can see at this particular picture, this is the water, and you have put a certain metal right on it. You can put your sodium or lithium. However, it is not as advisable to do these kinds of the experiments, right? So it is catching fire, and in that case, so all these reactions I have written over there. And the reactivity towards water for these alkali metals, it increases actually down the group. So lithium is the least reactive when it reacts with the water, and your cesium is the most reactive. And lithium hydroxide, as you can see here, it is a very weak base, okay, but all other hydroxides are highly basic in nature. So this is a very important reaction, so you should remember this particular point. All alkali metals are more reactive, okay, than your hydrogen, thus they are easily and readily oxidized water, right? And the reaction with water is so exothermic, okay, that the heat generator often ignites the hydrogen gas which is produced, right, which I have shown in this particular picture, okay. So the vigorous nature of the reaction with water for these alkali metals actually increases from lithium to cesium, okay. Lithium is only slowly attacked by the water at room temperature, and though it liberates more energy, it should be remembered that however lithium reacts very slowly but liberates more energy when it reacts with the water, okay. And sodium reacts rather vigorously, and potassium catches fire, okay, when you put the potassium when you put the potassium in the water. And rubidium and cesium reacts very explosively, so that's why these such kind of the reactions cannot be done by the students in the lab. So the fact that the lithium reacts with the water less vigorously, that means less slowly, it is probably due to the very high melting point, okay. Lithium is having the very high melting point, while other alkali metals are having the very low melting points, okay, generally below 373 Kelvin, okay, and they melt due to the heat liberated in their initial reaction with the water, thus exposing more metal surface to further attack actually, okay. The reaction therefore proceeds much more rapidly for the other metals than the lithium, okay, which is very important, while lithium remains almost in the solid state. So these much of thing you should remember when you react the alkali metals with the water. Now moving to the next property, what it says, okay, my next reaction is the reaction with the oxygen. So how actually these reacts with the oxygen, it is again a very important one, and lots of questions in the JEE main examinations actually comes from this particular topic. So here you can see the metal, and I am reacting with this metal with this oxygen, and this bond, right, metal oxide is formed, okay. And then lithium, you can see here I have reacted this I have taken the lithium here, so lithium reacts with this and produce your lithium oxide. It is monooxide, please remember, it is monooxide, so oxygen 2 negative is there, it is simple lithium monooxide. But with the same reaction, when you react sodium with this oxygen, then it will form the sodium peroxide, okay. And if you react your potassium, rubidium and cesium, right, then potassium forms KO2. However, all these things may form the your mixtures of the different kinds of the oxides, the oxides, superoxides and the peroxide. As you can see here, when you have oxide, that means the oxygen is in -2 state. In the peroxide, oxygen is in the -1 oxidation state, and for the superoxide it is in the -1/2 oxidation state. So whatever is written there in this particular slide is not in pretty much detail, so listen carefully what I am going to explain to you, right. It is very important, so please remember these things, okay. Alkali metals, when they are exposed to the air, okay, they readily reacts with the oxygen. See, later I will come to the other components of the air also, because air also contain your oxygen, along with the oxygen air also contains your water and carbon dioxide, etc. So the important thing is that when you are having a lithium, okay, so I can write here lithium. Say for example, when you are having a lithium and you are reacting this lithium with the oxygen, right, so it will only form your lithium oxide. It will only form the lithium monoxide, Li2O. If you want to balance this particular reaction, then you can take 2 of lithium and half of your oxygen, right. This would be the only product in case of the lithium, please remember, okay. And if you have, say, sodium, right, say I can write reaction here. If you are having the sodium, okay, and when this sodium is reacting, say, with the oxygen, okay, and the supply of the oxygen is limited, so I can write O here, O2 here, and it is limited. When the supply of the oxygen is limited, then in the limited supply of the oxygen it will form Na2O. That means monooxide. Please remember this thing, okay? And the same thing when you are having the sodium and the supply of the oxygen is in excess, sufficient supply of the oxygen is there, then it will form sodium peroxide. It is something very, very important you should know. Na2O2. Please remember, okay? And you see your other alkali metals, like if you have potassium in that case, okay? And generally if you treat this potassium with this with this oxygen, it will form your superoxide. Superoxide means like KO2. And similarly, if you are having a rubidium Rb and you are reacting with this oxygen, it will largely form the superoxides. However, I am not saying that it will only form the superoxide. You will get the mixture along with this your superoxide. You will also get your say peroxide and the oxide, monooxide also, okay? So these two you can see they are the superoxide, okay? And this is your peroxide, and these are your monooxide, right? So these reactions are very, very important, okay? So the formation and the stability of these oxides, whatever you are forming here, they can be explained on the basis of the lattice energy effect. If you know the lattice energy effect, then you will be able to explain why these oxides and the mixture of the oxides is forming. And lithium is always exceptional in that case. You know your lithium, if you are having the lithium positive, it is very, very small. Lithium is very small in size, so it can only cater very small size of the oxygen, okay? And that's why it is only forming lithium oxide, monooxide. So it cannot actually cater your other oxides like your say peroxide or the superoxide. So it is something very, very important again, okay? And you know the sodium and the rest of the metals are the very large ones, so they can actually stabilize the larger ion also. That's why they are forming your peroxides as well as the superoxides along with the oxide, right? This is again the same slide actually. This is your oxide ion, this is your peroxide ion, this is your superoxide ion. So if you are beginner here, right, and you are you have recently started learning inorganic chemistry, then these things are very, very important, like oxide, peroxide, superoxide, sulfate, sulfide, sulfide, nitrate, nitrite, nitrite, right? All these ions you should be able to differentiate between them in order to learn the chemistry, right? So whatever the alkali metal is there, right, towards all reagents the reactivity increases down the group. That means from lithium to cesium the reactivity with any reagent reactivity increases, but nitrogen is the exception. In the nitrogen the reactivity order is different. That means cesium to lithium, in that case cesium is more reactive and lithium is less reactive when you take the nitrogen as the reagent. See, you are reacting this with the air actually, okay? And air contains the nitrogen. You know the 78% nitrogen is there. So metal, especially the alkali metal, when reacts with the nitrogen it forms the nitride, okay? Nitride means N3, okay? So 6 of the metals reacting with the nitrogen and they are having NM3, okay? That means 2M3N. This is the formula, and you see the if you take the lithium, so 6 equivalents of the lithiums are required with to react with this one equivalent of the nitrogen to form the lithium nitrides, okay? So only lithium forms this nitride. Please remember, only lithium forms this nitride. So in that case only nitrogen is written here, but along with the nitrogen lithium can also react with the carbon to form carbides. So what I can do, I can write here lithium when reacts with the nitrogen, okay, it will form nitride, and lithium when reacts with the carbon it will form carbide. So lithium is the only metal in the group which can react directly with the nitrogen and carbon to form the nitride and the carbide. So despite having very high ionization energy, lithium is the only alkali metal which reacts directly with the nitrogen and carbon to form the corresponding carbide nitrides and the carbides. Okay, while other alkali metals do not react directly with the nitrogen or the carbon. So if you are having, say, your sodium and you are reacting directly with the nitrogen, then no reaction would occur. Similarly, if you are having the potassium and you are reacting with the carbon directly, so there would be no reaction. Please remember this point. You know, the lithium is very small in size, right? Lithium, if I take the lithium ion, right, it is very small in size. Or simply the lithium, you can take the example of the lithium only instead of the lithium ion, right? So it is having the very small size. So this is probably due to the fact that the small size of the nitride and carbon ions coupled with the small size of the lithium ions results in a very high lattice energy. That's why lithium reacts readily with the nitrogen and the carbon. Okay, and thus you know, the heat of formation of these compounds are much higher actually. Okay, and which results in the more stability. And my next property is reaction with the hydrogen. So your alkali metals, when react with the hydrogen, right, so see, that means if you take the mixture of the alkali metal along with the hydrogen and heat them together, it results in the metal hydride, right? Why metal hydride? Because your hydrogen is in negative oxidation state and metal is always positive. Okay, hydrides of such type like MH, like LiH, NaH, KH, right, except francium, while all other hydrides they are generally colorless crystalline ionic solids. Okay, and why they are ionic? Because I already told you this your hydrogen is negatively charged and metal is the positive charge, so it is ionic in nature. Okay, so hydride ion basically present in the crystal lattice. The alkali metal hydrides, all these hydrides actually they possesses the sodium chloride type of the structure. Sodium chloride type of the structure means coordination number would be 6. You know, in case of the NaCl, coordination number of sodium is 6 and coordination number of each chloride is also 6. So these hydrides are also having the same structure as that of the NaCl. Okay, and the ionic character of the bonds in the hydrides increases as the atomic number of the metal increases. That means down the group, if you go down the group, in that case ionic character actually increases because metallic nature also increases down the group. Okay, and the stability also increases in the same manner if you go down the group, right, like that. So stability also increases. So here down the group reactivity increases, as I already explained you, and stability also increases in the same manner, and ionic character also increases in the same manner for the alkali metals. Please remember this thing. Okay, but if you can check the data here, what the data is saying actually, your lithium hydride LiH, right, lithium hydride is the most stable. Why? Because it is having it actually dissociates only after your 1273 Kelvin. Here your lithium hydride, which is the most stable one, and it dissociates above 1273 Kelvin. So I can write here lithium hydride dissociates above 1273 Kelvin, while other hydrides dissociates below 773 Kelvin. Okay, so this is I have taken from the some standard book actually. Please remember this thing. And the most important thing which you should remember, which is not written here, all these alkali metal hydrides, they are very strong reducing agents. Okay, the alkali metal hydrides, they are very strong reducing agents, and their reducing property increases with decrease in the stability. Okay, please remember. So generally in that case, you see lithium is very important, right, in organic chemistry generally, right? When you do the organic chemistry, you must have learned about this very famous reducing agent, lithium aluminium hydride. Okay, or lithium borohydride, right? Lithium also forms these things. Okay, and that's why this lithium is very, very important. Okay, so this is all about the properties of the hydride, that means the reaction with the hydrogen. Now Let's move on to the next property, what it says. Okay, the most important one, by far this is the most important one, I can write here. And in your CSIR net examination, in IIT JAM, or in the GATE examination, you may have the question from this particular topic also, the reaction with the ammonia or the liquid ammonia. Okay, ammonia, that means you can put these metals in the ammonia also, right? And the reaction is very, very important. So what is written here, you see, all the alkali metals dissolved in the liquid ammonia giving deep blue solutions. Initially it is not deep blue, actually initially it is light blue when the concentration of the ammonia is very dilute, right? When it is in the dilute ammonia, the color is the actual light blue, and when you increase the concentration of the ammonia, that means if you keep on adding more and more ammonia, then the color changes from light blue to deep blue solutions. Okay, so here it is written, when dilute due to the presence of the ammoniated solvated electrons in the solution. So this is not actually right, this is not the exact correct explanation, right? I'm sorry for this one, because as I already told you a few minutes back, these slides are downloaded slides, not very up to the mark, please listen carefully what I am saying, because this slide is not the up to the mark. So first of all, you should remember this thing. When you heat this alkali metal, right, in the ammonia gas, somewhere around the 400 degree centigrade, right, and you have to add little of your iron, then the first reaction is the formation of the metal amides. Okay, this is the first property. First, in case of the first property, what you can do, say for example, you are having the sodium, okay, and you are having the ammonia gas. So first I am taking the example of the ammonia gas, okay, and in presence of little of the iron fillings, and temperature is somewhere around 400 degree centigrade. So it end up with the sodamide, NaNH2. But this is in case of the ammonia gas. See this reaction, your cesium is the most reactive, followed by the rubidium, and then your potassium is there, and then your sodium and lithium is least reactive. Right? This particular reaction is not there in this particular slide. That's why I have written the reaction here. However, the important reaction is there in the slide actually. Okay, now I am discussing the liquid ammonia. So all the alkali metals, they are soluble in the liquid ammonia, and they give you the solution which is highly conductive and blue in color. Sodium metal, right? I am writing here. See, you are having the sodium metal, and in case of the sodium metal, if you treat this sodium, if you put this sodium metal into the ammonia, like here NH3, right? If you put this into the NH3, then it will give you the things like that. First is M, NH3, so I am writing X here, okay, and I am putting positive over there, that means it is in plus 1 oxidation state. So this is actually this particular complex. And next is your ammoniated electron. See, NH3 and Y is here. Since this is electron, so I can put negative here. So these two species generally formed. And in that case, this is your cation, this is your anion, and they have the different functions. Okay, now you can see when what I told you, in dilute cases, dilute solution means less ammonia. When you put any metal like sodium metal, it will give you the light blue color. So what should be the reason behind this? For the reason is this ammoniated electron. So the color of the solution is due to the ammoniated electron. But if you increase the concentration, right, if you keep on adding ammonia to it, okay, then this color would be deep blue. So first of all, you should remember all these dilute solutions, right, only one electron is there. You can see here one electron is there. So if the solution is dilute, then it is paramagnetic in nature. Please remember, okay. Why? Because this free electron is there. Now if you keep on adding ammonia and make the solution more concentrated one, what will happen? The electrons gets combined and they form a pair. So this deep blue is actually diamagnetic. It is diamagnetic, and this one is the paramagnetic. So we have discussed the magnetic nature. So why I have introduced the magnetic behavior here, because it is very important. You should know that in the dilute solution the free electron is there, single electron is there, which gives the paramagnetic nature to this particular solution. When you keep on adding ammonia, the electrons get paired and the color also changes from light blue to deep blue, and the solution becomes your diamagnetic. So I can write color and I can write electrical conductivity. Color is due to the ammoniated electron, and conductivity is largely due to this cation along with ammoniated electron also. Both are the contributing factors. You must be wondering that why I am not actually giving the value of the x and y, which I am using frequently right here in the equation. So values of x and y, it will depend upon the solvation by the ammonia, right? It varies actually on the concentration. Okay, so this is again a very important one. And the solutions which are these solutions are strong reducing agents. Why reducing agents? Because they are having electron, right? And these electrons can reduce any other salts, reduce your metal halides, right? Metal halides to metals. Say for example you are having the metal halides and you are reacting this, then it will reduce to the metals. Similarly, if you are having your nitrogen oxide like laughing gas, so it will give you the nitrogen, okay, because it is the reducing agent. Similarly, if you are having say oxygen, okay, and you are using the same reagent, then it will give you this peroxide, okay. And then you may also think about this O2 negative superoxides or the peroxides also. So this aspect is very important. Birk reduction is there, so I'm not going to discuss the Birk reduction. Actually in the Birk reduction we use the same combination, the liquid ammonia and the alkali metal. It is a very famous reaction. If you are not aware about this particular reaction, you can go through the description box. I am giving you the link of the Birk reduction. I have also made a video on the Birk reduction. You can go there and see how it is acting. Okay, so generally these alkali metals they replace hydrogen from the oxidizing acids. So this is my next property, that means the reaction with the acids. And you know the acids are of the two types. First is the oxidizing acids, and second is the non-oxidizing acids, non-oxidizing, right? These two kinds of the acids are there. And your non-oxidizing acids are generally dilute HCl or your dilute H2SO4, and your oxidizing agents are the concentrated one, concentrated HCl, concentrated H2SO4, and your HNO3. HNO3 actually could be anything. It could be a dilute or it could be the concentrated one. In the both ways the reaction goes well actually, right? So how they can react? For example, you are having the H2SO4, okay, the H2SO4, and you are reacting with the metal. Say you are reacting with this food. So what it will form? It will form, of course, Na2SO4, sodium sulfate, and you will have the H2S gas, right? And then the water molecule. These reagents would be there. If you want to balance this particular reaction, then you will need 5 of H2SO4, 8 of Na, that means 4 of sodium sulfate, H2S is there, and of course 4 of water molecule. Okay, so here 4 and 1. Okay, this is the balanced reaction, right? This is important. Now suppose you are having your HNO3, you are reacting this with HNO3, and for example it is concentrated one. Okay, for concentrated acid you are reacting this with sodium. Again your 8 equivalents required and 10 of this required, because it is monobasic acid, right? So the value would be the double that of the dibasic acid, that is H2S. So it will form the metal nitrate. 8 of so I can write Na instead of this Na. So here this is 8 of NaNO3 plus your N2O and your 5H2O. Okay, so this is your laughing gas, please remember. And suppose your acid HNO3 is dilute, not concentrated one, that means it is having the water, so you will require 9 equivalent of this one, and of course 8 of your sodium, right? So it will not make any difference whether you take sodium or potassium or rubidium or cesium, the reaction always goes like that. Okay, NO3, and then you are having the ammonia, and then your 3H2O. Okay, so these are the reactions. So what important observation you can make from here: whenever your oxidizing acids are there, right? These all are your oxidizing acids, right? Concentrated H2SO4, HNO3, whether it is dilute or concentrated, it is not liberating hydrogen from the acids, but it is forming your hydrogen sulfide H2S gas, it is forming laughing gas, it is forming ammonia gas. So 3 gaseous products are formed. But if you put the metal in the non-oxidizing acids like dilute H2SO4 or dilute HCl, as you have seen earlier, they will quickly remove hydrogen gas from here, H2, right? You can write here nature of nitrates. Okay, so first of all, you know, in the last slide, if I go back, you see I have formed these nitrates, right? NaNO3 and NaNO3. So I am discussing the properties of these. So nitrates are basically your MnO3. It could be your LiNO3, it could be your NaNO3, it could be your KNO3. So their properties are what? They are colorless and water soluble also. And they are ionic in nature. Okay, and they do not actually hydrolyze. See, and a very important property is there. However, these nitrates of alkali metals do not hydrolyze, but they decompose on heating. Please remember all the nitrates except your lithium nitrate. So what I can write here, exception. I can write exception here, and this is your lithium nitrate, which I'll discuss in a little while. While see other nitrates, like if you are having the NaNO3, sodium nitrate, if you heat it, it will decompose to give you sodium nitrite, NaNO2, along with the oxygen, and same is true with the potassium nitrate also, KNO3. Okay, potassium nitrite with the oxygen. This is on heating. So whether you take the sodium, potassium, rubidium or cesium nitrate, they dissociate to give you the nitrites. So basically it is sodium nitrite. Okay, the spelling is NiTrite because it is NO2 negative. Don't write nitride, it is nitrite, not nitrite. Okay, while this lithium nitrate is the exception. If you heat this lithium nitrate, okay, then it will give you the lithium oxide, Li2O, and 2 of the NO2 will remove from here along with the half of oxygen. So this is something very, very important. So why actually this happens actually? So basically it is due to the more polarizing power of the lithium ion. Your lithium ion, right, Li positive, you know, it is very small, so its polarizing power is very, very high. Polarizing power is high, so it will polarize oxygen to form the lithium oxide. Okay, because you know the oxide is also a very small ion. Okay, so they actually interact to form the lithium oxide. So if you don't know about the polarization and polarizability and the Fajans rule, again you can check the description box. I am giving the link of the Fajans rules. Okay, I have also formed the sulfates, right? See, you see here nitrates. I have discussed the properties of the nitrates. Now I have also formed the sulfates. So it is very important to see the properties of the sulfates as well. Again, a very, very important one. And you know the sulfates of kind M2SO4, Na2SO4, K2SO4, etc. These are very common. Okay, these sulfates are basically water soluble. These sulfates are water soluble. But again you see here lithium sulfate Li2SO4. It is also water soluble, but its solubility decreases on increasing the temperature. Why? Because the reaction is the exothermic in nature. See, if you put H2O, if you put this into the H2O, and then it will form the solution, and it will liberate some heat. And since the reaction is the exothermic reaction, okay, and due to this exothermic reaction, if you increase the temperature of the system further, that will not, if it is exothermic reaction, that means it is liberating heat. The system is not required heat. If you supply the temperature, if you heat it again, then the solubility of the lithium sulfate decreases. However, in some of the textbook you will also find that the lithium sulfate is not soluble while other sulfates are soluble. It is not true. It is less soluble, but solubility further decreases when you heat the system. Okay, this is something again important point to remember. Okay, and another very important thing is that, see, these alkali metal sulfates, if you have say K2SO4, if you have K2SO4, it is a very such sulfates are having very strong tendency to form the double salts. They form the double salts. Okay, and they can form the double salts along with the with your say iron. They can form the double salt with the aluminium. Okay, and you may take the chromium also, right? All double salts can form. A very famous double salt, you know, K2SO4, Al2SO4 whole thrice, dot 24H2O. This is potassium, and it is a double salt. Okay, and this 24 order of crystallization is there, and many other double salts you can also form. But you see, lithium actually will not, see, it is forming alum. This potassium is forming alum, sodium can form alum, but lithium is not known to form the alum. So I can write this in the form of the question: why lithium does not form alum like potassium? Okay, again, you know, this lithium is an exception, and Li positive is very small in size. Okay, Li, it is very small, and to form a lattice of the double salt, so this lithium is very small, and due to the extremely small size of the lithium, it is not able to form a stable complex required by the double salts, or say the alum actually. Okay, so while you see potassium is larger in size, so it can stabilize this particular crystal lattice, but lithium, due to the small size, cannot stabilize this lattice. That's why the alum of the lithiums are not known. So these alkali metals are known to form the halides. Okay, so halides of kind Mx, and if you take the Mx, that means you are having the NaCl, you are having the KCl. Okay, and then you are having the other halides as well, etc. So these alkali metals readily form halides with the when reacting with the halogen. And if you know the coordination number of this NaCl, right? So sodium 6 and chloride is also 6. So 6:6. That means 1:1 ratio is there, and this whether it is sodium chloride or the potassium chloride, they will have this particular ratio. But exception is there. Say if you are having after potassium rubidium and then the cesium, say you are having the cesium chloride, not only cesium chloride, if you are having the cesium bromide or the cesium iodide, whatever the halide is there, okay, in that case the coordination number would be different. The ratio would be 8:8. So you should remember this point. For NaCl, for alkali metal among alkali metal halides, NaCl is having the coordination number of 6 of your sodium as well as the chloride. Okay, while in case of the cesium halides like cesium chloride, bromide, and the iodide, this coordination number is 8:8. Right? And why it is actually happening in that case? It is due to the more favorable lattice energy. In case of, see, if you have the lithium, theoretically it says that the lithium is having the coordination number is 4:4. If you have the lithium chloride, 4:4. But lithium can also form this particular ratio, 6:6. So guys, my next important compound of the alkali metal is are the alkali metal carbonates. So I can write the alkali metal carbonates. Basically they are the oxysalts. Oxysalts means the sodium, the salts which contains the oxygen. You know the alkali metal is electropositive, it can form the Na positive, and it can react with the carbonate to form the compounds like alkali metal carbonates like Li2CO3 I can write here, and then I can write Na2CO3, which is again like that, and then I can write K2CO3, etc. Okay. So these are the carbonates, these are the oxysalts. You may think of your bicarbonates as well. So these all are actually very stable. Please remember, these oxysalts are very stable. What is the meaning of the stability? The meaning of the stability is nothing. If you have the sodium carbonate, okay, and if we heat it, no reaction at all, okay. But if you take your lithium carbonate, Li2CO3, if we heat it, then it will break into the lithium oxide along with the carbon dioxide. So this reaction which I have written here, it is only possible in case of the lithium carbonate, while this reaction is not possible for the other carbonates. That means your lithium carbonate is the least stable and it is decomposing readily on heating. So why actually it is happening in that case? The only reason is that this cation, this Li positive, if I write in the form of, again you see the reason is same but explanation is different, but reason generally is same. So Li positive is there, okay, and this is small in size, so its polarizing power is very high, okay, and it can actually form the salts with the small anions, and you know the oxygen is a small anion, so this is rather more stable than this particular one. That's why it facilitates this kind of the decomposition. Okay, so whatever the gain in the lattice energy would happen, right, due to this substitution of the oxide ion from your carbonate ion, it enables the decomposition. The driving force of the decomposition is what? Gain in the lattice energy resulting for the substitution of the smaller oxide ion from the larger your carbonate ion. This is the reason actually. Bicarbonate, if you take the example of the bicarbonates, right, so bicarbonates like sodium bicarbonate, CO3, so all the bicarbonates of the alkali metals, again they can be obtained in the solid forms, so it could be it is solid. And similarly, if you have the potassium bicarbonate, it is also solid in nature, okay, but lithium is actually not like that. And all the carbonates or bicarbonates, they are water soluble, but lithium carbonate would not dissolve readily in the water. It would be less stable, or you can say the sparingly soluble. Anomalous behavior of the lithium. First of all, you know, very small in size, polarizing power is very high, that means charge by radius ratio, okay, and its ionization enthalpy is very high. That's why ionization enthalpy is very high. That's why it is formed the covalent compounds but not the ionic compounds. Electronegativity, electropositivity is very low. That means it is less metallic when compared to the sodium, potassium and others. Okay, this thing. Now next, okay, now the reactions. You can see in water, lithium is reacting with the water to form this solution LiOH, which is actually the weak base, while other metal hydroxides like sodium hydroxide, potassium hydroxides, they are the strong base. Please remember, this is weak base while rest are the strong base. Now if you react this with the air, lithium is forming only this particular oxide which I have explained, while other can form the oxides, superoxides or the peroxides. But you know the air, in the air your nitrogen is also present, so lithium can react with the with the nitrogen directly to form the nitride as well as the carbide, as I have explained in my last slide, and it can react with the hydrogen to form the hydrides. But lithium hydride is quite a stable one. Why? Because this lithium is very small in size and this hydride is very small in size, so it forms a very strong lattice. That's why it is stable. while you know the other metals are little bigger in size when compared to the size of the hydride, so their actually other metal hydrides are less stable. Then along with the halogens, you can see it forms the soluble metal halides, but lithium fluoride is insoluble while other are soluble, right? Now next, right, see this I have explained, lithium weak base, this I have explained, and least reactive, strong reducing. See, lithium, the air, lithium monoxide, lithium nitride, I have already told you. Lithium hydride most stable. So all these things I have covered. Lithium carbonate I have covered, lithium fluoride, and then the lithium phosphate. They all are the sparingly soluble. That means they are not readily soluble in the water. Next is lithium melting point and boiling point, right? Very high. It is a hard metal. Due to the hardness, metallic crystalline structure, high lattice energy. Okay. So, and lithium chloride is deliquescent. So now see guys, it is something very, very important. Hygroscopic, deliquescent. What is the difference between hygroscopic and deliquescent? It is again very, very important, and students should know about this thing. See, hygroscopic basically is the ability to absorb moisture, from atmosphere, and deliquescent means it will form liquid with the water. That is the deliquescent nature. Substances that dissolve in the water. How your substance is the hygroscopic, which is decide the deliquescent nature. So this thing you should know. So this LiCl is your deliquescent in nature. That means it will dissolve in the water to form. It will absorb the moisture and gets completely dissolved and form a solution. While your sodium chloride NaCl is there, it is hygroscopic. It will absorb the moisture, but it will never form the solution. Okay. And why this happens? Due to the very high hydration enthalpy. And then you see lithium nitrate, I have discussed, the decomposition is like that, while other will form like that. Okay, this I have discussed. And lithium carbonate I have discussed, it will give you the this lithium oxide. I have explained this one. For lithium bicarbonate, it will not obtain in the solid form, while other alkali metals would be obtained in the solid form. It will form your lithium imide. Okay, or while rest will form the amides. So this is again very important, which I have missed actually. Lithium forms the lithium imide, okay, while other forms the amides. And after that, again a very important aspect, that is the diagonal relationship. This lithium is there and magnesium is diagonally placed to this particular lithium. So that means the properties of the magnesium would be similar to the lithium. They have the similar properties. So the diagonal relationship is said to exist between the certain pairs of diagonally adjacent elements in the second and the third periods of the periodic table. So what is the similarity? Reason? Similarity in the ionic sizes and similarity in the radius ratio effect, charge radius effect. Atomic radii, if you compare, lithium is 152, magnesium is 160, they are very, very similar. If you take the ionic radii, again 76 and 72, very similar. If you take the polarizing power 1.7 and 3.9, it is, however, actually difference is quite high, right? And electronegativities are quite similar. Points of similarity between them. Lithium hydroxide is weak. Of course, magnesium hydroxide is also weak. Lithium forms the lithium nitride. Magnesium also forms the magnesium nitride. Okay, and you should know this thing, right? Magnesium is what? 2 positive, and your N is 3 negative. I can write like that. So it will give you the Mg3 N2 like that. Okay, this will come here and this will go there. Okay, and you see lithium is hard here, even magnesium is hard. LiCl is deliquescent, magnesium chloride is also deliquescent. So it is dihydrated, it is octahydrated. Lithium carbonate decomposes, as I already told you. Magnesium carbonate also decomposes. Lithium hydrogen carbonate, bicarbonate, cannot be obtained in the solid form. Magnesium bicarbonate cannot be obtained in the solid form. So these are the similarities. These are the crown ethers. This is 12 crown 4 if you number it, right? So I can write like that. Say this is 1, this is 2, this is 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this 12 is for the all total atoms. 4 stands for the oxygen because 4 oxygens are here. 1, 2, 3, 4. It is 12 crown 4. Okay. Now if you see this one, so 15 is there. You can do by your own. Say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. So it is 15 crown 5 because 5 oxygens are there. 1, 2, 3, 4, 5. So these are the crown. Similarly, you can do for this 18 crown 6 also. And you know this lithium ion, actually lithium ion can only be fit or the sit into this particular cavity, and that's why it forms the compound with this one. Here you see the lithium is fitted here, and then you see the potassium will fit here, and your cesium will fit here. 18 crown 6. Okay, so these are the alkali metal compounds, the important one. Along with this crown ethers, the cryptane compounds are also there, but I am not discussing the cryptane compounds here. Okay, I'll discuss this thing in the later stages. So what is the bioinorganic chemistry? For bioinorganic chemistry, you know the sodium and potassium, these ions are very important for us. So not only the sodium and the potassium, but alkaline along with this alkali metals, alkaline earth metals like magnesium and calcium are equally important for us. But in general, you should know your sodium ion, actually it is extracellular fluid. Extracellular fluid means if you see here, sodium is outside the cell here, extracellular ion, while your potassium is the intracellular ion. It is present in the inside the cell actually, and your potassium is found in the intracellular fluids, that means inside this, like in the cytoplasm. And see, substantial amount of sodium and potassiums are required, okay, to prevent the different kinds of the diseases. So see, whenever your sodium is present inside this intracellular fluid, it will be pushed out to the extracellular and it will require some energy. It will act as the potassium pump. So in the biological system, sodium potassium pumps are also there. So the biological machines, you should remember this particular point, the biological machines that are responsible for the selective transport of the ions, metal ions, okay, they are basically the very complex assemblies of the proteins, and they are known as the ion pumps, okay, sodium pumps or the potassium pumps. And these ion pumps actually recognize and discriminate between the metal ions in the same way as I have discussed for the crown ethers. That means in case of the crown ethers, in certain size your sodium is fitting, in certain size cesium is fitting. In the same way in the ion pumps also, right, in the proteins your certain ions can go in and out. And if some defects are there in the ion pumps, then serious diseases may result. Like for example, chloride ion is responsible for the kind of the disease. However, I am not discussing the anion here, but you should know about the other things also. Like say what I have written here, you see, hypertension. So in many cases, your hypertension, your high blood pressure, right, they are thought to be the defect in the sodium uptake or the excretion. That means you are say if a sodium intake is very high and excretion is low, then you may have such kind of the problems. If too much of the sodium is absorbed by your body from the diet and very little of the sodium is excreted, then what will happen? Water diffuses from the tissues into the blood, and blood gets diluted. Thereby this decreases the osmotic pressure in the circulatory system, and this will increase the blood pressure, okay, and it may rupture the arteries, right, and it may also result in the brain problem. And you know, the patients which are suffering from the hypertension, low sodium diets that use the NaCl substitutes like KCl are often prescribed. If hypertension is there, then you should take KCl instead of the NaCl. However, the taste of the KCl is same as the NaCl, but you will not require the NaCl when you have the hypertension. Okay, and one more thing, if you see, the potassium ion basically is not readily taken up by the body, so only limited amount would be present inside the system. Basically, this is the method to control the hypertension. However, it is debatable. So I hope you understood the things and you like the lecture. And if you are watching the video for the first time and you are a new watcher, so please subscribe the tetrahedron chemistry classes and do share the lectures with the friends also. Okay, and don't forget to like the video, and I'll meet you in the next class of your alkaline earth metals. So that's it for today. Thank you very much.